Lecture 30-something in probability. Hopefully it's going to track a little bit. Okay, so we started the day by looking at throwing dots at a piece of paper. I know there's a couple of people who took Calc 3 with me many years ago, and you might remember this, so if you do, please don't speak up. For those of you who haven't seen this before, why are we throwing dots at a piece of paper? Yes?
Because it's fun.
It's fun, yes. It also allows me to buy a dartboard and make that a business expense. You never ever underestimate the importance of that. What mathematical concept though, because it probably should be a mathematical concept, do you think this is for? Yeah, there should be something related to random generation, because we're throwing dots. What kind of assumption do you want to make? Don't look down here with the holes. What kind of assumption do you want to make about how the dots are hitting this paper?
That it's equally likely that the dart hits any point on the paper.
Good. So every point is equally likely to be hit. Now, what's the probability you hit a specific point? Yes?
Basically zero.
Basically zero. So the probability we hit any point is zero, so the probability we hit anywhere on the paper, we're just integrating zero over everything, which would just be zero, and that explains why we have some structural holes down here. Now, so a continuous distribution, the probability of hitting any point is zero. What you talk about instead is, what's the probability you land in a certain region? What's the probability we land in the top half of the paper? That would be a half. If we land in the upper right quadrant, a fourth. So what we can do is, the probability we hit any specific region is just going to be the area of that region. And this is why this is so important. So somebody asked what was on this. Caleb was too busy drawing nice artwork, and I couldn't be able to put any extra stuff on. So I drew kind of like a maybe smiling heart creature. And let's say we want to find what is the area of the heart creature. What we can do is, I'm going to assume that this is a unit square. Although you could do it if it was not a unit square, you could do it for other things. I'll take a new piece of tape. So I can look and see what fraction of the dots land inside the region. So if I throw n dots, I can count how many dots land in the region, divide by the total number of dots thrown, and that should be a really good estimate for the region. This is sadly how we integrate. This is sadly how a lot of Wall Street finance is done. This is called MonteCarlo simulations. There are some people who've called this concept one of the most important advances in computational mathematics in the 20th century. Stuff like this was used during the Manhattan Project in World War II to try to estimate a lot of very difficult calculations. You would have these monster integrals to do. And what you would do is essentially throw dots. Now, of course, in the real world, we're not going to be throwing dots at 180-dimensional space. What we're going to do is we're going to simulate. We're going to draw a point at random and see, is the point in the region? If yes, it's a 1. If no, it's a 0. Gee, what does that remind you of? What kind of variables? Okay, Bernoulli. Binary indicator variables. Yes or no, 1 or 0. All we need is that it's easy to tell if you're in the region. So if you have a couple of curves, and you can easily tell, let's say the simplest case, MonteCarlo integration. For simplicity, I'll assume it's a unit square. If it's not a unit square, what you would do is you would just rescale things. If this has area 5, you would then just multiply your fraction by 5. So let's just assume it's a unit square. Let's assume you have some curve, here's f of x, and here's g of x. All I need to be able to do is tell, if I choose my point, is it less than f of x, is it greater than g of x? If so, it's in the region. If not, it's outside the region. So we do not need to be able to do the integration with respect to the area under f of x, the area below g of x. If we could, we wouldn't be doing this. The whole point is, this allows us to integrate natural functions. So so long as it's easy to evaluate, is your xy coordinate in this range. Okay, so let's see how it works. All right, so let's say xn is equal to 1 if n tossed is inside and 0 otherwise. And then maybe we'll have, yn will be x1 plus xn, capital N. Is this what we want to look at, or do we want to look at something related to this? Yes?
You want to look at that over capital N?
Yeah, I want to look at the fraction of points that are in N. Right? So if I look at the fraction of points that are over N, because it didn't focus around. So if I look at the fraction of points.
It needs to be like tactical.
Yeah, okay, you can fix that. Thank you. So I want to look at the fraction of points, because that's going to give me the area. What do we think that this should converge to? What should this fraction converge to? As n goes to infinity, yn should go to what?
The area between curves.
It should go to the area. Right? The more points we take, the more accurate it should be. Okay. Well, what do you think yn goes to? For a very large n, what do you think yn looks like? Yn is approximately what? Remember, this is reviewing what we've done this semester, so what do you think yn is looking like if n is huge? Yes?
A normal?
It's looking like a normal. So we have to figure out what is the mean and what is the variance, right? Whenever we are given a normal distribution, we have to provide two additional pieces of information. Which normal is it? It's normal with this mean, it's normal with this variance. If I give you a chi-square distribution, what do I have to tell you? Degrees of freedom. If I give you an exponential, I have to give you the parameter lambda. So to finish naming this, so let's think of what's going on. The expected value of yn is actually equal to, well, let's see, the expected value of the sum is the sum of the expected values. So it's going to be n expected value of, say, x1 divided by n, because they all have the same expectation. And the expected value of x1 is just the area, right? Because it's 1 if the toss is inside. What's the probability it's inside? Since the whole region, the boundary region, has area 1, the area is the probability we're inside. So this is going to just be the area. The variance of yn, the variance of a sum is the sum of the variances. We have the 1 over n, so what does the 1 over n become when we do a variance? It becomes a... becomes what? 1 over n squared. If you multiply a number by 5, the variance changes by a factor of 25. It changes by that constant squared. Think about the units. If you change from, feet to inches, you change by a factor of 12. And so since the variance is the unit squared, it should be changing by 144. And then when you take the square root, you'll get the factor of 12. The standard deviation will just scale by that factor. So I have a 1 over n squared, but then I have n things that are identical, and then I have the variance of a Bernoulli. And it's just going to be p times 1 minus p when you do the calculation, or area times 1 minus area. So the variance is going to be the area, 1 minus area, divided by n. So if I take the standard deviation, it would be the square root of that. So I would have a square root of n and a square root of area Do you want the variance to be large or small? Small, right? The smaller the variance, the tighter you are about the actual answer. What do you think makes the variance small? Yes?
Either large n or area close to large, area close to.
Right, so we're going to assume n is fixed. And so since if we take a fixed n, then the closer the area is to either 1 or 0. So we're trying to find the minimum of the function area times 1 minus area. So let's say I give you the function h of x equals x times 1 minus x. Sorry. Does not want to swim today. All right, so how would I find the minimum of this function? Yes?
Take the derivative was 0 and check that it's minimum.
Anything else? Yes.
Yeah, check endpoints.
Thank you. I really don't want to crash into the wall again. Right? Have to check endpoints. Now, to take the derivative of this, I think it's actually better to expand it out as x minus x squared, so that we don't have to use the product rule. Then we would get h prime of x is 1 minus 2x, so the critical point is x equals 1 half. And if you check the endpoints, you have x equals 0 and 1. Well, at 0 and 1, you get 0, so 1 half is going to be 1/4. So the maximum variance is at 1 half. Maximum variance at 1 half. What shape is this? That's a parabola. So if you actually just recognize it's a parabola, here's 0, here's 1, it has to then be the maximum at 1 half. So the standard deviation is going to be less than or equal to, if I put in 1 half, I'll have 1 half times 1 half, which is 1/4. Square root of that is 1 half. So it'll be less than or equal to 1 over 2 square roots of n. The standard deviation could be smaller than this, but I know worst case scenario, the standard deviation is going to be like 1 over 2 square roots of n. So as n gets very, very large, this is going to be very tightly concentrated about the area. Okay? So if I want to get a better estimate of the area, what should I do? Take more and more points. So this is where the subject gets really interesting. If you know ahead of time how much computational time you have, maybe you can only run the program for 10 minutes. What you might do is you might choose a very nice lattice so that you're sampling the whole region uniformly. So maybe I do, 1,000 points by 1,000 points. That'll give me 1,000,000 points to look at. Or maybe I do 10,000 by 10,000. What happens if you now find out actually the program ran a little bit faster than expected? You can run it for another 10 minutes. Where do you put those extra points? Well, one thing is you could, of course, just completely choose the points uniformly at random. And if you do that, you don't have to worry about anything like this. But there is the possibility of having points clustering in certain regions. If you do a lattice, that assures that you will sample the space uniformly. If I know the lattice you have, is it possible for me to jerry-rig my region to miss? Absolutely. So there's a lot of different games you can play. If you do the dots, if you throw the points completely at random, you're in great shape. But you do have the tendency, you might be oversampling in some regions and undersampling in another. So a lattice approach is often used. But the disadvantage is that you have to, if you're lucky enough to have additional runtime, you don't necessarily have a great way to put in those extra points. It turns out you can use something that's almost like a lattice, something that's got structure but a little bit random, involving Fibonacci numbers, where you're putting in points randomly related to the Fibonacci numbers. And then if you have additional runtime, the points just add in a good natural way, so that you just run it for however long you want. And so I'll put up some links as to how you do something like that. For our analysis, we will assume we're throwing the dots at random. Okay? So now, this is going to converge to a Gaussian. So the normal with mean area and variance at most 1 over 4a. And now what you can do is you can build confidence intervals. If I run the program and I have an n this large, what's the probability I'm within a certain amount of the true area? Say I want to be within, 0.01. I can get an upper bound by assuming worst possible case the variance is as large as possible. I might be doing much better because the variance could actually be a lot smaller. But this is at least one possibility. Okay? Any questions on this? So this is one of the most important applications of the central limit theorem. It allows us to estimate areas of very painful regions very quickly. And, square root of n is not that bad. So let's take a region. So this is where I'm going to ask you to tip the, I want it to be able to see, maybe you want to turn off the lights, we'll see if that works well. You hit the light switch. Oh, I didn't see that. See if I can move this far enough over here. Alright, so if I do it like this so that that's going to trap me.
Yeah.
Alright.
It doesn't want to focus.
It doesn't want to focus?
Yeah, no, it's really blurry.
Is it focusing at all now?
No.
You want to try putting on the light and seeing if that helps the focus? Is it helping at all? Or? If it doesn't work, then that's the...
I mean, everything's blurry. I don't know why.
Alright. If it's not working well, it's not working well. Was it better with or without the light?
It's the same.
It's the same. I will leave the light on then. Alright. So I have here a region. A blue point means it is outside the region. A red point means it's inside the region. Okay? So here's a couple of points. Alright, hopefully it's somewhat focused and
No,
not
you
at all.
literally can't see anything.
Sorry.
Sorry.
It's fine. But that's the whole reason I'm doing it this way, not having it focused on me, was so that I could capture the video. Alright, so I will just post these slides. Anybody recognize what region this is? I'm sorry? A circle? You don't think it's something like 3 clover leaf?
Enough points to tell.
Yeah, there's really not enough point to tell. Now, there is this running thing up here, which is, this is 2 by 2, so the area of the whole square is 4, and the fraction times 4 is 3.30435, and we've used 23 data points. So do you still like to guess of a circle? I'm sorry?
That's pretty good.
Yeah, so what would be the area of a unit circle? 3.14. And we've got 3.30 with 23 data points. Well, it seems like it's a little bit that maybe. So let's get a few more data points. What do you think now?
That's pretty good.
Area is 3.11111. Circle and non-circle. But you can see that as the points are coming in, there's vast regions where we don't have any sampling. And this is the problem when you throw things randomly. There will be large holes like this. But let's let it run a little bit more. And it's beginning to fill in a little bit. Alright, what about now? Is it beginning to look like a circle? Now it's 3.20. And you can begin to see like there's some kind of boundary here going like this. There is no blue at all inside this big region. And the blue is just on the boundary. And so now, let's run it a little faster. And so we're speeding it up. You can see the area is now 3.1, and it's fluctuating around 3.1. I'll go a little bit faster still. At this point, it should no longer be too hard to guess what region this is. So this is now almost 4,000 points. Right, a little bit over 4,000 points. At this point, I think it really is looking like a circle. Looking like a circle. But you can see this sizable pockets where we have absolutely no information. And this is the problem of choosing points like this. So I will try to just jump ahead to here's 6,000 points. Here's almost 8,000 points. And the answer we're getting is 3.16. What do you think? Okay, so now Everybody close your eyes for just 1 second, because I'm too far away to, okay. Keep them closed, okay. Keep them closed, actually keep them closed. Okay. All right, wake up now, okay. So let's see if you can guess what region this is. Any thoughts? And the area is about 1.33. So let's put a little bit more. And whenever you have a guess, shout it out. So speed it up a little bit.
Uniform region.
Okay, so what possibility? It's maybe a uniform region in some kind of band.
Yeah.
Now this blue point here is as high as some of these over here. So I don't think it'll be a rectangle. But there definitely seems to be red is concentrated towards the middle. But you can see there's huge sections where we are not getting points. If we were to use a grid approach, we would have a lot more information at this point.
So like, maybe like an ellipse or something?
Maybe like an ellipse. So since that's a damn good guess, let's speed it up a little bit. And tell me when you start to think it is an ellipse. Is this enough information to think that it looks like an ellipse? Oops. So I'll speed it up faster. And you can really see the pattern emerging. And this is now on the order of 5,000 points. But so I'll stop. So here's around almost 8,000 points. Again, you can see large regions of white where we're missing things. And so we are oversampling in some regions. Over here, this is extremely dense red. We've got an area about 1.577. Yes?
Are there the same number of points in both regions? Because both times it seemed like the smaller region to more dense points.
Over here,
On the circle too, and the
well,
corner edges, it seemed a lot more dense.
a lot of this is random fluctuations, but we do not expect to have the same number of points inside the ellipse because the whole square has area 4. The ellipse seems to have area around 1.5, 1.6. So there should be fewer points that are red than blue.
Am I crazy to think that the red points just look more dense?
Yeah, I thought the same thing. I thought blue was more like yellow. I don't know.
But I mean, it's tough because you've got some pockets here, you've got some pockets here as well. It would be an interesting experiment to go and do a more detailed statistical analysis to see if it is more clustered in the region than out. The denseness should be equally distributed between them. Anybody recognize the number 1.57 or what that's close to?
It's like roughly the golden ratio.
So one thing is roughly the golden ratio. The golden ratio is around 1.6. Anything else that's near this? Yeah.
Pi over 2 is close.
Pi over 2 is close. Now, if we're going with an ellipse, which would you go with? Pi over 2. Why would we go with pi over 2? It's related to a circle. So what I want to do for the rest of the day is I want to talk a little bit about how we would do some integration and change of variables. So this is essentially reviewing Calc 3. And then from this, we will go and switch to... is it somewhat focused on me?
Oh, there it is.
Excellent. So we will review some Calc 3 and then we will do Buffon's needle. Have you ever heard of Buffon's needle? Right, this is a great probability problem that has been used to fraudulently calculate some things in the past. Okay. So, area of ellipse. We could do this in 3 dimensions as well. We could do the volume of the ellipse. I'll just do the area. And this is a way to somewhat review the change of variable formula and multivariable distributions. Okay? For those of you who are continuing in statistics, they really want to make sure that you're comfortable with joint distributions, joint densities. That's one of the reasons why I want to talk to this. Now we have a conjecture that's related to pi. So the fact that it was pi over 2 is probably related to the fact that we chose the semi-major axis to have a equals 1, and maybe the semi-minor axis equal to 1/2. So if I have a circle like this, let's call this A and B, and let's have an ellipse, and let's call this A and B. What's the area of the circle? And I guess you could also call both of these R. What's the area of a circle of radius R? Pi R squared. What would you guess the area of an ellipse is? Pi AB. And in the special case when A equals B, that should reduce to a circle. If I give you a sphere, what is the volume of a sphere? 4/3 pi R cubed. What would you guess the area of a ellipsoid?
4/3 pi ABC.
Probably 4/3 pi ABC. Right? So again, if you can reduce something to a case you already know, that's a great way to start. All right, so how would we prove something like this? Well, let's look at what the equations are. So write this up here. Pi R squared, pi AB. This is x over R squared plus y over R squared is less than or equal to 1. And I use different variables. U over A squared plus B over B squared is less than or equal to 1. And I'm just trying to write them in similar manners. Okay, so let's see how we do the integration. So the integral over all u and v such that u over a squared plus v over b squared less than or equal to 1 of 1 du dv. Okay, we really don't want to do this integration. We want to somehow change variables. Okay? What's the easiest circle to understand? The unit circle. So let's come up with a change of variables. So I want to pass from UV coordinates to XY coordinates. What should I send U to? So if I want a unit circle, I want x squared plus y squared to be less than or equal to 1.
Yeah.
So send u to what?
AX.
I don't think it's ax. You're close. So if I take my value of u, then you're saying x is equal to u over a. All right. We'll do it. Okay. So I want u to be ax. And you want b to be by. Let me do it like this. So now our equation u over a squared plus b over b squared is less than or equal to 1. This becomes x over, becomes x squared plus y squared less than or equal to 1. So we've now converted it to a unit circle. Do we know what the area of a unit circle is? Yeah, it's just pi. So now, let's do the calculation. So we have to figure out how the area element changes. So we want to figure out what does du dv go to? Well, if u is ax, what's du? ADX. And so this would get du dv goes to AB dx dy. So the integral of 1 du dv over the ellipse, how does the function 1 change if we change from uv coordinates to xy coordinates?
From AB.
I'm sorry?
I mean, oh, 1 doesn't change, right?
1 doesn't change. This is the nice thing about integrating a constant function. 1 has no u and v dependence, so I don't really give a what I change u and v to, it's still 1. So So now my bounds of integration become the circle, and now I have 1, but now my area element is now just AB dx dy. So this would then become AB, and the integral over the circle of 1 dx dy, and that's just pi. You get pi AB. And that's why in the case we looked at, the answer was going to just be pi over 2, because A was 1 and B was 1/2. So what I like about this is we were able to numerically guess the formula by just doing a simple code and a simple simulation. How many of you have actually calculated the area of an ellipse before? Okay. How many of you have calculated the perimeter of an ellipse? Okay. This is an extremely difficult problem. You have to introduce new functions to calculate things such as the perimeter of the ellipse. I was reviewing a calculus book many, many years ago, and they had an explicit formula that was nice for the perimeter. I think I made a branch in one of my Calc 3 classes about this, is I knew that they were not doing a good job choosing exercises because there's not a nice formula for the perimeter of the ellipse. You have to introduce new, difficult functions. But this is the power of simulation. I wrote a very simple mathematical code. I will make the code available. We gathered some data. We looked at a simple case first with circle, then we moved to the ellipse, and we said, we could vary A and B, and for different values of A and B, we could actually make a table and then try to guess how it depends on A and B. What you would often do is you would hold one of them constant and vary the other and see how that's scaling. So if you start off with A equals B equals 1, you would see it's around pi. And then you would say, if I double B, if I half B, I see how things change. This is why I really want you to get to the point where you can write simple code. And then we were able to do the multiple integration by reducing it to something we already know. This is a technique we have done over and over and over again this semester. Right? Whenever possible, I try not to integrate. I always try to make some kind of claim, this is very similar to something we've already done. And since it's similar to something we've already done, I don't need to do it. And I can just reduce this to the answer. Think of all the times we've done normalization constants. Right? Where we show that this integral has a functional form that I can identify with a probability distribution. So that integral has to be 1. So whatever the constant is that was floating around from the other calculations, that has to be whatever I need to make this a probability distribution. So a lot of times you can actually get out of doing painful integration if you can reduce it to something unknown times something you understand very well. Okay. Any questions on Monte Carlo? Okay. So what I want to do now is I want to switch and I want to do Buffon's needle. How many of you have heard of Buffon's needle? So I first learned about this when I was an undergraduate at Yale. I was one of the co-presidents of the math club, and we had 2 jobs: get pizza and get professors to give talks. And in fact, because both presidents my year had class right beforehand, we couldn't actually get the pizza, so we created the position of secretary, which we gave to pre-med students who could then put on their resumes when they were applying to med school that they were an officer in the math club. Worked very well for everybody. So I need to get talks, I need to get speakers. So I'm trying to convince my probability teacher, who I really like, to give a talk. And I said, we'll provide free pizza, we'll do all the setup, we'll do all the cleanup. Yes, all right, I'll give a talk. And this is where I learned you should be very careful what you promise and not give blanket statements. So he gave a talk on Buffon's needle. So there's a lot of different variants. The simplest is, imagine you have an infinite grid, and the separation between all the grid lines is D. Okay? You then take a rod of length L. And for simplicity, we will assume L is less than D. And what you do is you drop this rod on the infinite grid. And it's as likely to land anywhere as anywhere else. And you look and see how many times, if you do n drops, does it intersect the line. Why do you think I want to assume L is less than D? Yes?
Because if L is greater than D or too much much greater than d will always intersect the line?
No, I could drop it straight down like this and this. You're right that it has to do something with the intersections.
So it doesn't intersect two lines?
It doesn't intersect two lines. Now, it's possible I could drop it perfectly like this and have infinitely many points of intersection, but the probability of that is 0. I'm not going to worry about it. If the rod was long, however, I could drop it at an angle and it could hit multiple lines. So I'm going to assume I don't hit multiple lines. So what he did is, we had a tiled floor, which had a nice grid structure, and he had a box of spaghetti, and he opened it up and he threw the spaghetti in the air, and I had promised to clean things up, and he said, now we can count how many intersections there are. And this is where he really killed me. He then reaches, and now, of course, let's see if it matters if the spaghetti is dry or wet. And he then threw wet spaghetti and got some of it to actually stick to the ceiling. I had to give him credit. He put me really bad on that one. How would I calculate what the probability of an intersection is? I have to first figure out what do I want my variables to be? What do I want my coordinates to be? So when the rod hits, without loss of generality, I want to be able to make some kind of simplifying assumptions to reduce the calculation to something that's manageable. I don't want the rod landing at any point in the whole plane. Is there any simplification I can make? How can I view the rod? Yes?
You could view it as a one-dimensional problem, and the rod is just like a one-dimensional line that falls on the line.
Okay, which line does it have to fall on?
Line perpendicular to all the dividers.
I mean, there's infinitely many lines perpendicular to all the dividers, but let's just take one of them.
Yeah.
Let's take the line y equals 0. Without loss of generality, we may assume the rod lands on the line y. Which point may we assume lands on the line y equals 0?
The midpoint.
The midpoint. So without loss of generality, midpoint of rod is on the line y equals 0. That greatly simplifies the analysis. So again, that's one of the hardest parts in a problem like this, is you want to move it down to a manageable calculation. Now I have the rod lands here. What variable do you want to introduce? Or variables?
You would introduce the theta that intersects the line.
So one is the theta that intersects. What else do I want? So one of my variables is going to be theta. There's another variable I need. I need two variables.
Nearest, distance to nearest.
Yeah, so one thing is distance to nearest. So again, symmetry is absolutely wonderful. What can you assume about the angle without loss of generality? Probably 0 to pi, or maybe even 0 to pi halves. Right? Because if it's landing like this, well, it's going to be the same as reflecting it down like this. So we can assume 0 less than equal to theta less than equal to pi over 2. Right? I could have theta go all the way up to 2 pi, but it's not needed. What should I assume about the x-coordinate? Where does the x-coordinate live? 0 less than equal to x less than equal to d over 2. Because if it lands closer to here, I can just flip things. So again, we don't have to do this, but this makes things a little bit easier. And so now what we have is we're going to have two uniform distributions. So both are uniform. And now what we need to do is we need to calculate what is the probability that a rod with a given value of x and theta intersects a line. How many points of intersection could we have? 1 or 0. We are going to ignore the possibility that x equals 0 and theta equals 0. I'm sorry, theta equals pi halves. We're going to ignore that possibility because that happens with probability 0. So we have either 0 or 1 intersection. So we have to figure out, given x theta, does it intersect? So we'll have f of x theta be 1 if intersect, otherwise 0. And so now, what's the integral we need to do? It's going to just go, x goes from 0 to d halves, theta goes from 0 to pi halves, f of x theta, d theta, dx. Well, what else might we want to do? We might want to switch the order, right? That's one of the most powerful techniques we have. So now we have to figure out what is f of x theta. So here is 0, here's d over 2, here's d. So we land here. Here's our midpoint. Which is the only line that this could hit? The left line or the right line? The left. So we want to figure out when is it close enough and long enough to hit. So how would we do this? Well, the whole rod length is L, so this part over here is L over 2. Right? So if I want to figure out the distance I'm traveling here or the distance I'm traveling there,
L over 2 times the cosine of theta.
it's L over 2 times the cosine of theta. And if that's greater than x, it hits. So if L over 2 cosine theta is greater than x, it hits. Because L over 2 cosine theta is going to be the length over here, which is the same as this length here. Right? And then that would mean that the x point down here would be past this line. So this is the region we need to integrate over. So you got a 50-50 chance. Right? Given a value of x, this tells you what value of theta, or given a value of theta, this tells you what value of x. Which way do you want to integrate first? X or theta? Let's do x first. If you do it the other way, if you do theta first, theta is going to be 2x divided by L, and then take the arc cosine of that. If you would like to take arc cosines, please see me afterwards. You need help. Okay? You do not want to be putting arc cosines in your integration bounds, right? Your first instinct should be to avoid the arc cosine. Thank you. All right, so now let's try doing it the other way. So theta goes from 0 to pi halves, and then x goes from what? So we want x to be less than, or less than or equal to L over 2 cosine theta. So what's the smallest value for x?
L over 2. Oh, smallest value is 0.
Smallest value is 0. If it's on the line, we're definitely going to hit. Now, given a value of theta, what's the largest value of x we can take and get an intersection point? We need to find our range of integration.
L.
Not L. L over 2 cosine theta. Right? That's our condition here. So L over 2 cosine theta. And now we just integrate the function 1 dx d theta. All right. What's the integral of 1? It's just x. Then we evaluated L over 2 cosine theta minus 0. So we get the integral. Theta goes from 0 to pi halves L over 2 cosine theta d theta. And you can see that this is actually not going to be a bad integral. If you were to do it the other way, if you're bored later today or you want a challenge, try doing it the other way. And so now if we do this, this is then just going to be all right, so okay, yeah. So then it's going to be L over 2. What's the integral of cosine? Is it sine? Okay, so we get sine of theta evaluated at pi halves and 0, and what's sine theta evaluated at pi halves and 0. So we just get it's equal to L over 2. All right, so hopefully this will shift. Oh, good, shifting. So now, that's going to be the area. What do we need to divide this by? So the probability is L over 2, and what do I have to divide it by? So what should I divide this by? So this gives the area of the region in x theta space. What's the shape of my x theta region? What kind of shape is it?
Well, it's a square, right?
It's a rectangle. So if I put x down here and theta down here, x goes all the way up to d over 2, theta goes all the way up to pi over 2, and then I have the curve, x is less than or equal to L cosine theta. I've got something in here. I don't care exactly what it looks like. And so I want to figure out what fraction do I have. So this is the area of the region. I have to divide by the total volume, which is going to be d halves times pi halves. So we get d pi divided by 4. So I get the probability, if I've done it correctly, is L over d times 2 over pi. So whenever you see a formula, you want to check and see, is this reasonable? As d gets very large for a fixed value of L, what happens? It goes to 0. What's the maximum probability? Well, if L equals d, we would get 2 over pi. Is 2 over pi greater than 1 or less than 1? Less than 1. Good. I should not be getting a probability larger than 1. If I double L and double d, what happens to the probability? It stays the same. In fact, we should have guessed before we did any calculation that the answer has to be a function of just L over d. If we change, we talked about this earlier, if we change from feet to inches, it's not going to change the probability. So the answer should be a function of just L over d. So this has a lot of great features to it. So people have used this to calculate pi by throwing rods on grids and counting intersections. One of my favorite examples is somebody who did this. They calculated pi to, I think, 8 decimal places correctly. Surprising or not surprising? And it was with a modest number of tosses. I think the number of tosses was in the 300s. What they did is they looked for a really good rational approximation to pi. And they threw that many rods, and threw should be in quotes, and claimed they had that many intersections. And what someone noticed is, gee, if you'd thrown one more rod or one fewer rod, no matter how it would have landed, your accuracy would have gone down by 3 or 4 digits. And so it's not a proof, but it was highly suspicious that this person was cheating. But this problem has a lot of nice features. It's how do you set up the multivariable integration? How do you choose the order of integration? How do you define your variables? The last thing is, and I don't think we have time for it, so I'll send a link. There is a way to do this problem without integrating. What you can do now, just quickly sketch it, is imagine you have a bunch of rods, all very, very small, and you put them down in a circle. If you choose the radius of the circle to be d over 2, the circle will hit exactly 2 rods. And each one of these is going to give you all the different angles. So I'll send you a link as to how this is made rigorous. You can actually get the answer without actually doing the integration. It's one of the most clever ideas I've seen. All right, so we will continue doing review classes like this.